And next speaker is Sergei Lamzin, and we are moving to afternoon's favorite topic, RW Auriga.
Hot topic.
Sorry.
Yeah, it's okay.
Окей, да? Хорошо. Hot topic. RW Auriga is a young binary. The distance between component is a couple of hundreds AU, so they are far. Here you see the parameters of both components. They are more or less comparable. And the most interesting feature of this binary is sudden Demings events, which started in 2010 and continues up to now. It was this. You see this picture many times, but let me pay your attention. This is, let's say, yesterday. So the effect continues, and polarization, as was said, increased up to 30% in I band, and in V band it was 20% in minimum brightness, and it is assumed that this is the consequence of flyby of the companion RWUB near the primary, which occurs approximately 500 years ago. And you saw this picture. Stefano showed it, I guess. And the second consequence of this flyby is jet, which has appeared probably also 500 years ago, and this is in agreement with the idea of Repus, the interaction of components in double system triggers the accretion events that produce powerful outflow. But it was found recently from our observations that the secondary also has a disk. You see continuum image, and this disk is a bit less than circumprimary one, but comparable in size. Sorry. Here we present results of our photometric, spectral, polarimetric observations of B component. And here you see light curve of B component, so this resolved, spatially resolved observations. So we observe light curve from U band to K band, and you see chaotic variations of the star. So RW Auriga B is also a variable star, and with amplitude is in V band of 1 magnitude, and there are some kind of dimming events. In the next slide, they are shown in more detail, and you can see that during one night, 1.5 day, let's say, brightness fall down 1 magnitude. So if to look at histogram in different bands, then one can see that from U to J band, it looks like that the star varies around some bright states, but sometimes some dimmings occur. But in K band, the situation is completely different. You see that star more faint, and sometimes some kind of increasing of brightness occur. H band is some intermediate between these two cases. Variations of colors are also different in this optical and infrared band. One can see probably some bluing effect here, but maybe not, I don't know. Pay attention on the amplitude of variations, but here, so you see then the star became red when it became fainter, but in the infrared band the situation is opposite. Here is polarization measurements of B component, and here you see that when the star fades, its polarization increase up to 2-3%, and here is shown the direction of jet of A component, and this is the large axis of the disk, 90 degrees difference. And you see that most usually, like in most uxors, position angle is oriented along large large axis of the disk. This is in contrast to A component, where polarization was oriented along the jet, I mean perpendicular to the disk. So the first conclusion is that I was invited with this topic because B component is UX Orionis type star, and so its photometric variability occurs due to eclipses by dust, of course gas dust clouds, and we published paper devoted to A component, and it was our conclusion, as Peter told, that it is, in the case of A component, that the reason of dimming is dusty wing. So if we have the same situation here, but probably not, we have 3 spectra at our disposal, observed in 1998 to 2015 and 2016. And we derived effective temperature from titan O molecular band, so of the B component. Here you see it, and we used our observation as well as archival data to make set. Here you see 2 curves which illustrate if we use spectroscopy made easy model and BT settle model for 2100 temperature. They are a bit different, but and AV, I forgot to plot this, is twice larger than in the case of A component. We derive this one. So we see that there is some near-infrared excess, so probably we see the disk of the component in agreement with ALMA observations. In general, the spectrum of the B component is absorption one, but not too much emission lines are present in this spectrum. And we see some accretion signatures in Balmer lines. You see these dips. 3 colors corresponds to 3 observations, to 3 spectra. We see and equivalent widths of H alpha about 4 angstroms, but Duchenne observed equivalent widths of H alpha order of magnitude larger. In calcium-2 and helium lines, we see narrow components, emission components, which indicate the presence of powerful chromosphere. And what is the most interesting from my viewpoint is the absence of the wind signature in any emission lines. And we see a profile of oxygen-1 line, forbidden line, and it is narrow, probably this is disk wind, very low intensity disk wind due to X-ray evaporation. But I show you this picture, and you see that this is two components, and you see jet A from A component, but there is no jet from B component. So why? There is interaction, both stars have disks. Why B component has no disk, and what is more, no trace of intensive wind as well? The answer is, I don't know. In fact, there are a number of examples when we have highly accreted stars, single stars, let's say, DI Cepheus or BP Tauri with very large accretion rates without jets. So it's not trivial why in some cases we observe jets and why not. At least accretion rate is not the main factor, or the only factor, let's say. So we have no measurements of magnetic field strength in the case of B component, but it's known that powerful chromospheric activity occurs. We have seen this, and we know that the star is very bright in X-ray, more bright than A component, so B component is more bright. Bolometric luminosity, X-ray luminosity in X-ray band, 0.1% of bolometric luminosity is very high. So powerful corona is definitely present, and probably it means that the star indeed has magnetic field. Maybe something wrong with topology of this magnetic field. I don't know, but we would like to present some alternative explanation why disturbance of the disk of the component didn't produce jet. I refer to papers of other persons, so don't criticize me. MHD simulations of jet launching made in binary systems, Sheikh Nazami and Fent, suggests a critical angle between disk plane and orbital plane of somewhat above 10 degrees, beyond which a jet cannot persistently be formed out of disk wind. You have outflow, but not jet. Würter and Bate also received this similar results. They found that bipolar outflows are launched in only 10–15% out of 100, more than 100 simulations. And these models have strong magnetic fields that are initially parallel to rotational axis. Okay, yeah. It supports the idea of Fent and Zinnecker, who considered a certain degree of asymmetry as essential ingredient for jet launching. Not simply outflow, but just collimation of the outflow. And Rodriguez found, as was mentioned yesterday, that inclination of disks are different of both components. So disk A and B components are misaligned by 12 degrees. And so our conclusion, if it is conclusion indeed, possibly B component has no jet due to relatively large inclination of inner regions of its disk to the orbital plane. Thank you for attention.
Questions, please.
Is this system RW reader a case over chance flyby, or it's a balanced system?
It's a good question. Modeling was made as a parabolic motion, so it's something like this. But there are reasons, from my viewpoint, to suppose that it's very elongated, very eccentric binary with period 1,000, 1,050, 500 years, something like that.
Then I have a follow-up question. If there is such a period, what is the closest approach?
Maybe Stefano. Where is Stefano?
60, 70.
60,
Yeah.
70. Then the jet might be this knotted jet that we have seen in the image might be a reflection of this orbital periodic approaches and bursts.
Indeed, and yeah, it is.
But they did
But the
a-
question is, why there is no such jets from B component? There is from
that's
A.
another question, yes.
No.
The point is that whether the jet spacings agree with the periodicity.
No. The largest node correspond to dynamical time just 500 years. So there was during these 500 years, from today and back, where some additional ejections occurs.
I had a show of hands. I have a sort of small comment that what can we learn from the fact that probably all the old data of this binary star, even though it's 1.5 arc-second separation, is combined. We have long-term photometry, which is a combine of the
Sorry, once more, I don't know. The separation is 1.5 arc-second. Yes.
So probably all photometry of this object is a combine of them both.
All archival photometry, yes, but we observed from 2014 resolved photometry of both components. So we have, in the particular, we know that A component dimming was larger than 5 magnitudes. So when we see only 3 magnitudes dimming, in fact, we see, we started from this period, we see B component, and A component falls even. So we have both photometry, polarimetry, and spectroscopy resolved.
Yeah. So the lesson here is that when we see it separately, of course you analyze it separately, but we may have many of the targets what we are observing elsewhere, which we are not separating the binaries, and we get the multiple effect. So this is a good sample where you can separate it, but there might be other binaries which confuse us with this phenomenon.
Like usually ordinary binaries.
Yes. Any other comments? Yes, Benjamin?
In the image where you show the jet, there is a sort of shock structure to the left. Does it belong to the jet itself, or is an artifact? Yeah.
You mean this one?
Yes.
Yes, this is bow shock. This is bow shock, and its dynamical time is 500 years.
Okay, let's thank Sergei.